Steinhauer here. Welcome back. This is an exciting day in this astronomy class because we are officially graduating from the introductory material, learning the physics that we need to know to understand how astronomical objects work, to actually applying those concepts to real astronomical objects. And that will start with stars, and in particular, my favorite star in the universe, that is our own sun. There are two chapters in the book that cover the sun, chapter 15 and 16. I'm actually going to cover them in reverse order. And so this will begin our study of chapter 16, the sun, and particularly what makes the sun go, what powers the sun. And that's our goal for this chapter and for this class. So an important question is, how long is the sun going to last? And this is a fundamental question. And believe it or not, a little more than a century ago, it was not even one that we knew the right answer to. We've only understood the sun in the last 120 years or so as we have begun to understand how atoms work and how much energy there is in those things. So if you want to ask the question, how long will the sun last? There's a couple of things you need to know. The first thing you need to know is how much total energy is available in the sun. And the second thing you need to know is how fast the sun is using it. Now, it turns out that the first one is kind of complicated to get the answer to. The second one is a really simple answer to, and we can measure it directly. It turns out that we can look at the surface of the sun and measure how much energy in total the sun is emitting over time. This has to be also, therefore, how much energy the sun is generating. And so we've talked about this concept a little bit already in this class. The amount of energy that an object gives off per unit time is called its luminosity. You might remember luminosity has units of joules per second or watts. And in fact, a 60-watt light bulb consumes 60 joules of energy per second. Well, the sun, of course, is a much brighter light bulb than that, but we can measure that number directly. So how fast the sun is using it up is simply the sun's luminosity. And so it might be confusing. How are you going to use these two information? We might have, even if we can calculate this, how much energy is available, how are we going to know how long it lasts? Well, this is a fairly simple thing to do, but it's not conceptually obvious in this context. A very similar problem probably is conceptually obvious to you. And I want to make that analogy now. So asking how long the sun will last is equivalent to asking doing the gas tank problem. And the gas tank problem asks how long your tank of gas will last, right? And this is something that you have everyday experience with, and you can probably answer this question without even plugging it into your calculator or using a formula. You just understand how this works. So here it is. If you have a full 20-gallon tank of gas and you burn through gas at a rate of 5 gallons per hour, how many hours will the tank last? Go ahead and answer the question. You probably don't even need the formula. You just know how to do this. Okay, so you probably said, hopefully, 4 hours, right? If you have 20 gallons and you burn through it at 5 gallons per hour, how long will it last? You divided those two numbers. The total amount of energy you had divided by how fast you were using it up. And that's exactly how we're going to calculate how long the sun will last. Total amount of energy available divided by how fast you're using it up. In the gas tank problem, let's just do the units. This is gallons per or this is just gallons in the top. This is gallons in the top, and it's divided by gallons per hour on the bottom, right? The gallons cancel out, and you've got 1/hours in the denominator, and this just gives you an answer that is in hours. In the case of the sun, we're going to have joules of energy available divided by joules per second, and the joules are going to cancel out, and that's just going to give us a number that is in seconds that we can convert to any other unit we want to. That's how this game works. Okay, so what does power the sun, and how do we know, and how long is the sun going to last? Well, first we need to know what powers the sun. And this we didn't know 100+ years ago. We didn't know what powered the sun. And this was actually a major problem in astronomy because we could do some calculations and make some speculations. What if the sun is on fire? It kind of looks like it's on fire. There's some problems with this assumption and that there isn't much oxygen to make a fire go in space. But if we could get around that, and let's say the sun were made of something that's entirely combustible, like wood chips or coal or something that burns chemically fairly well. How much energy does this give off? Is this available to the sun in that case? And then divide that by the luminosity to get how long it's going to last. It turns out that if you take out the entire sun, and we're talking about huge amounts of mass were available to burn, let's say by coal or something, divide that by the present rate at which the sun is shining, you only get a number that's about 10,000 years. That's shockingly small, right? We know the sun is way older than that. So it cannot be that any chemical process like burning is actually happening to cause the energy on the sun. It's just not possible. Okay, here's an interesting one. Our next best guess 120 years ago for what could be powering the sun is that it was contracting. And this may seem a little bit counterintuitive, but you know you can get energy out of things with its potential energy. What is potential energy? If I lift a heavy object high above the ground, I am increasing that object's potential energy. If I let that object go, then that potential energy is going to be converted into kinetic energy as it falls towards the ground, right? And so you can convert, if you have a lot of mass that's suspended high above something that has gravity, like another mass, like the sun itself, then you can turn that potential energy into other kinds of energy, kinetic energy or thermal energy. And that energy can be then radiated away by the sun. And it turns out that there's a lot more of that kind of energy available because there's so much mass in the sun than there was chemical potential energy, even if that was a thing, which it isn't on the surface of the sun. So it turns out that you can calculate how much energy is available from potential energy. You can generate a lot of energy. You shrink the total size of the sun by a couple of meters. That's generated a huge amount of energy, as it turns out. Obviously, this can't last forever because soon the sun will be so small that it won't work anymore. But it turns out even bringing the sun from a fairly large size down to its present size could have generated quite a bit of energy. How much energy? Enough to power it for about 25 million years, right? That's pretty good. But we knew 120 years ago, scientists did, that the Earth and the sun were probably a lot older than that. In fact, there were geologists who were telling us that they were discovering rocks on the surface of the Earth that were billions of years old. So 25 million years is good, but it's at odds with other scientific facts that we were discovering at that time. And this is a big problem, right? If we don't understand how the sun can have lasted as long as it has, there's no way to coincide that with a very old Earth. There can't be a very young sun and a very old Earth. It just doesn't work. So that also isn't the answer to what is powering the sun. And it took the modern physics revolution of the early 20th century for us to figure out what was actually going on, and specifically understanding how atoms work and how nuclear fusion can happen. So what does power the sun? There are a couple of excellent videos by They Might Be Giants, which I will post below, that sing about this. The first of which is What Makes the Sun Shine, which is adapted from a 1950s or so educational song video about what makes the sun shine. And it's the sun is a mass of incandescent gas. That's the name of the song, and that's one of the lines in the song in the chorus. Interestingly, I'm sure that it was pointed out to They Might Be Giants as they were singing the song on their tours, that the sun, the surface of the sun is actually so hot that it isn't even a gas anymore. It's a plasma, which just means that there are charged particles running around. And so it behaves a lot like a gas, but it also behaves in somewhat different ways from a gas as well. And so they made a sequel to Why Does the Sun Shine, which is The Sun is a Miasma of Incandescent Plasma. Both of them are fantastic songs. I'll post them in the supplemental video section below, so you can check them out, and please do. So the answer is nuclear fusion. We'll talk about what nuclear fusion is in a bit, but it turns out that simply by combining hydrogen atoms together to make helium atoms, you can have a huge amount of nuclear potential energy just in the core of the sun, just in the very center part of the sun. You divide that amount of energy by the luminosity, and you get a number that's 10 billion years. And that is comfortably older than the oldest rocks that we've found on Earth. In fact, we think the sun is a little less than 5 billion years old now. We're about halfway through the sun's lifetime in terms of how much fuel it has available. Okay, we will come back next time and talk about how exactly what nuclear fusion is and how it works, and how the sun actually makes this happen. Okay, see you then.